Good afternoon. I'm sure most of you are getting tired of listening to me talk to you on a computer screen, but that's what has to happen. Today we are going to look at how to communicate enthalpy changes. We've talked about a little bit about it, some notation issues, etc. But there are four basic methods of communicating enthalpy changes, and we're going to look at them. Now they all are similar, but they're also slightly different too, depending upon what type of notation that we have. So our learner outcomes: define enthalpy and molar enthalpy, write balanced chemical or balanced equations, which include energy changes. You'll hear me say thermochemical equations. As soon as I throw the word thermo in there, you must include energy as a product or a reactant. We'll talk about the delta RH notation in communicating and analyze energy diagrams. Those are the four processes that we're going to use. What is molar enthalpy? What are thermochemical equations? What is the delta RH notation? And what are potential energy diagrams? You don't have enough time to copy some of this down. There are notes online that will allow you to do that in the classroom under completed notes. This is, I believe, lesson 5 in that set. Okay, so enthalpy is a product or reaction in a chemical equation. This is what we call a thermochemical equation. We're going to include energy within the equation. Now, if we think about our definition of exothermic, energy is given off to the environment in an exothermic reaction. Therefore, energy is a product of that reaction, and we write it as such. An endothermic reaction, energy has to be added to that system to get the reaction going. Therefore, it is a reactant in that system. Okay. So, two definitions that we had there. So if you have those two definitions, not that hard to think about where we're going to write the equation. Energy is given off. So an example like this case, it's a phase change where we have liquid water, steam becoming liquid water, and energy is a reactant or a product in that equation. You ever stuck your hand in steam, you know your hand gets hot because it's absorbing the energy as the steam cools down to liquid water. In this case, this is a combustion of methane. Combustion of most hydrocarbons all hydrocarbons gives off energy. And we write the energy change in the product. Now, what that means for this, we're going to use the balanced reaction. 890 kilojoules is given off when we react one mole of methane, or we can read it differently. 890 kilojoules of energy is given off when we create 2 moles of water. Okay, so this balancing here has to do with that energy. If I doubled this equation, so if I went 2, 4, 2, 4, this would become 780 because we're balancing based upon how much of the reactants are being used. Twice as many reactants, twice as much energy. Makes sense. So we don't write this as kilojoules per mole. We write it as based upon what is the balancing of that reaction. So as I said, if I double this, I'm going to double the energy at the end. And then endothermic, here, so we have to add energy to melt lead to become liquid lead. It requires 4.78 kilojoules to melt 1 mole of solid lead to become liquid lead. You have to add that, otherwise it doesn't happen. And here we have the decomposition of glucose. I must add almost 1,300 kilojoules of energy to decompose 1 mole of solid glucose. to melt or to decompose 2 moles of solid glucose, I would need twice as much energy. So balance that with a 2, that's going to become 2,540 kilojoules of energy. And these would be balanced double also. Now, molar enthalpies we've already talked about. This is the energy change per mole, whether it's an exothermic reaction or an endothermic reaction. It's per mole of whatever we are reacting. Okay, so fusion of water. So basically, this is the amount of energy required to be removed from water to turn it from liquid water to solid water. And molar enthalpy of methane is 890 kilojoules. Now you saw that a couple slides back, both of those, or no, one of those. Okay. We wrote it at this one here as a thermochemical reaction, 890 for 1 mole of methane. But we don't have to write it that much if it's a combustion reaction. So how do we distinguish between endo and exo? An endothermic process needs energy to be added to the system, hence a plus sign. An exothermic reaction loses energy from the system, therefore a negative sign. And so we briefly touched about this. So by convention, negative means exothermic. It does not mean anything else in terms of mathematics. It just means energy is leaving the system. And then if we're talking about an endothermic, we're positive. So water turning into ice is an exothermic reaction, so we would write it like this. Delta HM, now the SOL tells me what is happening. Solidification is negative 6.01 kilojoules per mole. If I'm going ice to water, which is an endothermic process, I must add energy to the system. Again, my notation would be delta fusion HM, so basically fusion telling me I'm melting it. It is a positive 6.01 kilojoules per mole. So both of those tell me what process is taking place, and that's telling me how much energy. The combustion reaction, we would write delta CHM, negative because it's an exothermic reaction, and it's 890 kilojoules per mole of energy given off, and that's exactly what that says. Now the C here tells me combustion. We don't have to write a chemical equation for that because we should all know what combustion is, the reaction of a substance with oxygen to give the most common oxides. And we should be able to create the chemical reaction for that. Okay. Here are our notations that we'll use. These are the 3 ones that we do need to know. We need to know a formation reaction, creating it from its elements. Delta FHM, now that symbol there just means at standard conditions, which is 25 degrees Celsius and 101.325 kilopascals. Sorry, that's not right. 25 degrees Celsius, 100 kilopascals. We don't usually use that too much, but you might see it. Simple decomposition is another reaction I expect you to know. It's the compound breaking apart into its elements. These two are reverses of each other. And finally, delta CHM, a combustion reaction. So every other reaction has to have a chemical reaction going with it. This is neither a formation, a combustion, or a decomposition. So I have to write the chemical reaction. The notation, delta RHM, R for the reaction. The substance that we're talking about per mole, so it's the creation of methanol. So here I read this, here's the reaction. To create 1 mole of methanol, I would get out 129 kilojoules of energy because negative, exothermic. So the notation, the reaction type, enthalpy change, the molar is the molar enthalpy. Standard conditions, as I said, are 25 degrees Celsius and 100 kilopascals. And then this XY on the bottom is what substance am I talking about? What substance am I talking about for moles? Which one is it in here? I shouldn't probably say reactants because this is products here, because this is a not a simple formation, but a formation. Never mind there itself. So there's the idea that you would have to use that. I have to give you the equation if it's not a combustion, simple decomposition, or formation. Now the other ones, solidification and fusion and vaporization, those are phase changes. We don't talk about them very often, but we can write those little subscripts for those. So here is another, if I was to interpret this, to create or to combust 1 mole of C3H7OH or propanol, I would receive 221 kilojoules for every mole of this substance that I react. Okay? I don't know what the rest of it is, but I know if I have 1 mole of this, that's the amount of energy I get out when I burn it in enough oxygen. Okay? These are examples. So this, okay, so here, there's our molar enthalpy. Here is our thermochemical equation for this. I've interpreted it in 2 ways. One, I've used fractions, 9/2. I still am only reacting 1 mole of the propanol. I'm getting out 2,000 kilojoules. If I balance it with integer coefficients, I'm going to get out 4,000 kilojoules because I am now combusting 2 moles of the propanol. If I was to double that, I would get 8,000, and so forth. So that's how I interpret the molar enthalpy into thermochemical reactions. Now, enthalpy change is very similar. The last one is delta RHM. This is delta RH, and it is very similar to a thermochemical reaction. It's depending upon how we balance. So these two down here, these numbers here, dependent upon how we balanced it. The delta RH notation or enthalpy change notation also depends upon that. You must have a balanced chemical reaction, and we're going to use this idea here. If we know the molar enthalpy, how many moles, that's going to give us the enthalpy change, the heat change. Okay, so here is water. There's a chemical reaction. We've balanced it 2, 1, 2. The molar enthalpy of this is 285 kilojoules per mole negative. So with this balancing here, the delta RH notation would be that. The chemical reaction, delta RH is equal to the negative 571.6. Because I have balanced it with 2 moles of water, I need to double the molar enthalpy. Notation here is in kilojoules, where molar enthalpy is in kilojoules per mole. Similar, but make sure that you don't double molar enthalpy. A potential energy diagram is a visual representation of energy change. Exothermic reactions means energy has been lost from the system, and the potential energy diagram is going to indicate that. If it's lost from the system, that means the products have less energy than the reactants did. So the bonds holding the products together have less energy stored than those holding the reactants together. Here's a very basic one for a phase change. We have a title. It's a diagram it's a graph without scales, essentially what it is. Along the y-axis, we have the potential energy change. Down here, I know it says reaction progress, put time. I don't know why I haven't changed that. We have the reactants listed here. The reactants listed here, the products listed here. And this says that we've had to add that energy. Now, here I've got delta EP is equal to 40 kilojoules. So the fact that it's rising means that I've added 40 kilojoules because it's increasing. You've got more energy stored in the potential energy bonds of the gas than you did in the potential energy bonds of the liquid. Basically, what we should know. We either write it in molar enthalpy or molar heat of reaction. Very seldom will you see this. Most often it is how the equation is balanced. So the change in energy for the reaction. You must include the reaction in the diagram. So here's for the potential energy diagram for the formation of water. We have our potential energy in kilojoules. We have our reaction progress. We have our title. We have our reactants listed here. We have our products listed there. I know that this is an exothermic process because my reactants have more energy stored than my products do. And how much more energy is over here. Now I've used delta EP. We can use a bunch of different ones. Nothing works right when you're sick. We can use delta EP or we can use delta RH, which my computer doesn't want to work. Now again, I could quite easily put a negative sign in here, it wouldn't be wrong. It's just communicating the information twice because my potential energy diagram is already telling me that this is an exothermic reaction. So we're going to just quickly go through this. I'm going to only do cellular respiration. Okay. We are told that 1 mole of glucose is consumed during cellular respiration to release 2,803 kilojoules of energy. I want to write thermochemical equations, delta RH notation, and potential energy diagram. So I'm going to start enthalpy of reaction notation. So let's get out of this and go here. So first of all, we need to write the reaction. So we're talking about cellular respiration. So glucose is C6H12O6, solid. I don't know if it's in the body. I'm going to add oxygen to it. Okay, because cellular respiration, this is one thing that you should have memorized. It's just the opposite of photosynthesis. And that's going to give me CO2 gas and H2O liquid. And this is important here. This is a biological process. And biological process is the water forms liquid. In a combustion process, if I was just burning glucose in on a table or something, I would get gaseous water. But in a biological process, we get liquid water. Now the delta RH notation depends upon how I balance this. So I'm going to balance it with that. Therefore, my delta RH notation is going back to my question, is negative. Okay, to release, hence the negative, the 2,803. The negative 2,803.1 kilojoules. Okay, if I had balanced this with a 2, 12, 12, 12, being lazy, my delta RH notation would be negative 4,600, nope, try that again. Would be 5,606.2 kilojoules. So the delta RH notation requires you to make sure you're balancing it right. Now, the thermochemical reaction, energy is released, energy is a product of this reaction, so I'm going to put it on my product side. And I'm going to add it, okay? That negative just indicates it's exothermic. By putting it on this side, it tells me it's exothermic. I don't need to stutter. So I'm going to add 2,803.1. I don't need to repeat myself by putting a negative sign there. You don't want to put a negative sign in this case. Now, this is a combustion reaction, so I don't need any of these reactions. I could just go the delta CHM of glucose is negative 2,803.1 kilojoules per mole. Okay? And that, again, we got that from 1 mole of glucose is consumed into release. So when you release is the negative, 1 mole. So this statement here is giving me my molar enthalpy of combustion for glucose. So I don't need these two processes are separate up here. This is just a third way of doing it. And my fourth way of doing it is a potential energy diagram. There are 2 ways to do this. Change. My change in my potential energy is going to be in kilojoules. We have an exothermic process that's going to look like this. Again, I'll explain to you what that bump is in a bump in this potential energy diagram in a couple of days. C6H12O6 solid 6O2, so I need to include my states of matter and basically my reactants here. My 6 CO2 gas and 6 water here. Now, a couple ways of writing this. I basically like to say, okay, going from here to here is 2,803.1 kilojoules, for delta RH is equal to, again, you don't have to, I find this is the best, the way that I like and the way it shows up quite regularly on a diploma or an exam. Another way would be this. I'm being a little lazy. Name delta T or delta EP in kilojoules. Okay, I would have my reactants here, my products down here, and this would be 0. This would be 2,803.1 kilojoules. So that comes across to there. So 2 different ways of writing it where we don't have any scale here. And if we do have a scale, it's just generally our 0 and then wherever we're going. Sometimes I might, if I do the reaction, I might put an energy there for readings later on, but that's generally all it is. Okay, there's your homework for today. Again, I'll spend a little bit of time going over this when I get back, because I know this isn't exactly the best way to deliver. However, it is what it is for right now. I shall hopefully see you tomorrow.